Okay, I think we should start then, Al or Brett. Who's going first?
Sure. I'm happy to be in front of the large crowd that we have attending late in the afternoon in the UK, and I I am joined this morning by my esteemed colleague Brett Quinn, who will talk about more of the storage complex and how that plays into a complete cyber shield for your mainframe. And I'm Al Surratt. I'm with Maintegrity. And this little picture of me on horseback in a raging river is a little bit in keeping with where we think, current mainframe security folks are. They're in the middle of a torrent, and their objective is to get to the other side. And what they need is help. So,
yeah, busy right now.
If you just click on for me, Brett, one slide, I'll go over the topics that we're going to go over, and then it'll be over to you. The rise of cyber resiliency requirements. I'm going to add a little bit in my section about the urgency around that. But this is primarily, what do you need to do to make the most critical element in the entire processing environment for your company? How do you make that rock solid reliable in the face of cyber security threats that are new and have never been adequately managed before? So with that, I will turn things over to Brett Quinn, and in a few slides, he'll turn things over to me. Thanks very much.
Thanks, Al. So I'm happy to be here. I want to talk today about what it takes to build a cyber shield for your mainframe data, and why do you need one? It's probably the place to start, which is the rampant rise of cyber threats and the frequency of them. As you can see on these slides, there's some notes in the bottom about where the source of this data came from. It's admittedly a bit old, and if anything, things have gotten worse. Every 11 seconds there's a cyber or ransomware attack costing globally in 2021 $6 trillion. And this column on the right shows, what's the average cost of cybercrime for an organization. And if you look at the footnote, that's 2019 data. So it's only gotten worse. And the focus has really increased for mainframe customers about what they should be doing to protect themselves in terms of being able to recover and also prevent cyber attacks. So bad actors are out there looking at all sorts of systems, and again, can hack anything from your iPhone to any networks that connect your iPhone to the servers that provide the data that you need for banking or healthcare or whatever. Distributed systems, however, seem to be a very popular place to launch mainframe attacks. This often contains a lot of the same data that the mainframe sources, but it is also a launching pad and has become so in recent years for attacks to be launched on the mainframe, which is, of course, the holy grail, right? When they asked at least something, why do you rob banks? Because that's where the money is, was the answer. And certainly mainframe systems are the most rich target for a lot of these hackers. So let's talk a little bit about what we're here to talk about today, right? It is my belief, and certainly I know Al feels the same way, and there are others in this area of interest of cybersecurity that feel the same way, that there are opportunities for different parts of the infrastructure to work together in ways that haven't been required before to produce a really robust security perimeter around your data and protect your data from cyber attack. And those areas are the data itself and where it lives, which is the storage array, the security infrastructure that's wrapped around ZOS and the applications, which is a discipline and a pillar unto itself, and DevOps and the processes to deliver the software infrastructure that is your applications and your vendor products. Those three areas don't necessarily work together in most shops. But I think it's important to note that if those three areas of technology, security, storage, and DevOps work together, and vendors work together to build solutions, we can create a real shield for your mainframe data. So I'm going to talk about the storage elements, Al's going to talk about security and DevOps, but it kind of makes for strange bedfellows. I don't know that we've ever had this level of integration or requirements for integration between these three disciplines of data security or storage security and DevOps in the past. But this threat for cyber attack is bringing us together. So let's talk first about the data and the storage layer, so to speak. The NIST cybersecurity framework, part of the U.S. Department of Commerce, has laid out a framework of 5 pillars of what you need to be focused on when building a cybersecurity and cyber resiliency solution. DORA in EMEA is the same, uses the same elements of identify, protect, detect, respond, and recover. And this kind of highlights the basic tenets of every one of these pillars and what they are focused on in the NIST cybersecurity framework. So what I'm going to do is I'm going to go through at the storage layer, admittedly using Dell products as an example, but I don't mean to just focus on Dell products here. I'm using them because I work for Dell. But there are similar functionalities that you can find in other storage vendor products. And I'll just use ours as an example, but it's not meant to be prescriptive as the only way this can be done. The first area we're going to talk about is protection. And how do we protect the data so to make sure that you can conduct a recovery should you need to? And in the Dell product line, there's a Data Protector for Z Systems product that has a 2-actor security feature. We'll talk a little bit about that. But the concept of making multiple copies of the data at some regular frequency is an important element of ensuring that you have the ability to recover data should you be attacked. And of course, there's the recovery disciplines themselves that are built into the products, right? The ability to restore data from the copies that are made, and a lot of partner tools that we have and tools that IBM has to be able to recover data. Integrity, of course, is a partner of ours that has tools that can recover data that is stored on various storage arrays, including Dell's. And we'll spend a few minutes talking about these 2 areas of protect and recover and what that means in the storage layer. And then I'll go into, at the end, detect before handing it over back to Al. So we talk about what can be done in the protect pillar. The concept here is of virtual or physical vaults. And the concept of air gapping, whether it's a physical air gap or a virtual air gap, is really important here. The notion here is that either at your production site or at your DR site or at both sites, as is shown in this picture, and we have some customers doing that, you need to make copies of the data, whether it be disk data, online data, or offline data, tape data. You need to be able to make copies of those that are not addressable and can't be altered. They are immutable. Immutable snapshots is a term that you'll hear us use. And the idea here is that you make, at some frequency, copies of the data that are not directly addressable by the operating environment so that they can be preserved in a state that will not allow them to be changed or deleted unless the system that's creating them does the deletion intentionally. So the idea here is that you make point-in-time copies of disk and tape data at either site, and you use them as recovery points should you have a cyber attack that corrupts the data, encrypts it, or alters it in some way, or deletes it. You have the ability to recover close to the point of corruption. And the storage complex, the storage infrastructure, has the ability to do this in a very space-efficient way in many cases. So in this case, I'm showing you an air-gapped, virtually air-gapped system, but also you can do a physically air-gapped solution where you have a separate environment that has a connectivity that can be enabled or disabled to provide isolation, which is a critical element, whether it's virtual or physical isolation. The ability to isolate the recovery source data is very, very important. So in this physical cyber vault, users can conduct selective recoveries. They can do a catastrophic recovery of the entire environment and send the data back. They can inspect the data. They can validate that the data is good on a periodic basis. A lot of interesting and useful things can happen in a physical cyber vault. And this discipline is well understood on the open system side, where data is sent as backup data into a vault, very, very common implementation. And in the mainframe space, it's a combination of 2 things. It's a combination of backups represented by the tape library depicted here, the BTL, and it's also copies of basically online data that is very close to the current state of the data, maybe in measures of minutes or potentially hours, but very, very close. Not last night's data or last week's data, but very current data can be stored by the storage layer in making multiple copies with great frequency. So that's a layer of protection that has never really been available before because it was too expensive. But with the advent of new technologies that have been introduced, certainly by Dell, as an example, the ability to make very frequent point-in-time copies is really not that difficult, and customers are doing that. The concept here is that the storage layer can create, either at a remote site, as depicted here, or at the local site, multiple snapshots of data, and multiple storage vendors have this ability. And take these snapshots at some frequency, whether it be 5 minutes, 10 minutes, 30 minutes, or on an hourly boundary, get you multiple point-in-time copies of data from which you can conduct recoveries. So that if bad data went into the environment and corrupted some of these snapshots, there would certainly be a very recent, most current good copy of data, and you could use that as a source of recovery. And that recovery would be a lot faster from that point-in-time copy than trying to go through the process of restoring data from a prior night's backup and then applying all the work again to bring the data current. So you have enough depth to be able to discover a corruption, and it can be very, very granular and not really very expensive with modern storage infrastructures. So the idea here is to create multiple point-in-time copies of data, whether it's on a disk, which is the more frequent, or it could be on tape as well, to give you multiple recovery points. So the protection is there, provided by the storage array, but also gives you a source for recovery. So when you're looking at cyber recovery storage-based solutions, you really need to look at the space efficiency that they offer, giving you a common pool of storage to reduce the complexity of making these copies, and automatically create point-in-time copies that don't consume a lot of space. So the technology is available, certainly in Dell's products, to make these copies very, very space efficiently and make them very frequently. Where you want to look for solutions that allow you to tune it from maybe minutes to hours, as I mentioned, and make a large number of snapshots and keep them potentially over several days, and then keep them weekly for maybe a month or more. The ability to do that is readily available in modern storage arrays. Most importantly, you want to look for solutions that provide immutability for the data and also make it secure so that it can't be deleted prior to its expiration date by a user interface, right? You mark something secure, it should stay secure. So those are good attributes to have in storage solutions. Also, the notion of two-factor security or dual control is another term used for this, where privileged insiders can't make changes to the protection mechanism itself. The storage array has a mechanism to create these point-in-time copies. It can be set up with definitions. Shouldn't be able to change those definitions at will by a single person, right? We don't want to have one person have the ability to neuter the protection rather, that the storage array is providing. So we are protecting against insider attacks. We're protecting against the coercion case by requiring two people to be able to make a change in the protection provided by the storage array. We call that two-factor security, good attribute to have in storage solutions. And of course, you want to be able to minimize the time to return to normal operation. And doing that means that you really don't want to be moving data around. So you want to look for solutions that don't copy data in order to create the protection. You want to be able to have readily accessible data that can be restored by only copying data that's changed and not having to make a full copy of data to reconstitute a prior point in time. You should be able to reconstitute a prior point in time very, very quickly by only maybe either moving pointers around or just moving changed data, or ideally not moving any data at all and just changing pointers. And there are solutions in the marketplace that can do that, make multiple copies of the data readily available without having to actually move data to make the copy available for use. So that's a quick walkthrough of protection and recovery that the storage layer can provide, give you multiple point-in-time copies of data that can be used for recovery in the event of a cyber attack. But the last element, I think the most difficult element to solve in the cybersecurity framework, what I call the holy grail of the NIST framework, is detection. How do we detect the data is going bad? Well, the storage array actually has an ability to do that. And there are vendors working on this. Dell has provided a solution very recently in this space called Cyber Intrusion Detection for Z Systems that uses the capabilities of the storage array, and uniquely only the storage array can do this, to let you know when data is being accessed in an unusual way. What Cyber Intrusion Detection for Z Systems does is, using capabilities of the storage array and also host software, determine what the working set size is of a data resource. That resource could be a storage group, a data set, or a device. And the idea here is to understand what is the normal amount of tracks in terms of the cardinality, the number of tracks in a given interval of time. Could be an hour, could be 30 minutes, whatever you like. What is the total number of tracks that are accessed? And we call that the working set size for that resource, for that workload, or that data set, that storage group. This is very different from the I/O rate. It is not the I/O rate. It's something only the storage array can provide. What is the unique track access count for this unit of time? And the idea here behind ZCID is to track that information, allow the user to report on it, and determine, well, what is the normal access rate for this workload? And how many tracks should be touched during this period of time or this day, this time of the day? And write rules, and through the monitoring that ZCID can provide, monitor these track access rates and determine whether or not the access rate is outside the norm, and issue a message to the user indicating that, hey, this is outside the norm. You should go look at what it may be accessing this data. The idea here is to just send up a flare, tell the user, hey, there's something wrong with the way this data is being accessed. You should go investigate. And the storage array is in a unique position to do that because it understands what the I/O rate or the access rate is for an individual data set or volume and can report on it. So detect is the next phase, right? The detect pillar of the NIST framework is the hardest one to solve. We're going to see a lot of activity in this area in the next few years. But here's an example of what Dell has done to provide a way to try and detect intrusions and let customers know when they're happening. So that's a view of the storage layer. I'll pass it over to Al and let him talk about security and DevOps.
Thank you very much, Brett. I'm just going to get my screen shared here, and then we'll get right to work on finishing up the presentation here, and then we'll come back for questions and any closing thoughts. So Brett gave you a very good overview of how important backup is, and adequate backup and timely backup. It is the primary asset that you have in recovery. But what we really feel is not only do you need strong recovery, you need prevention. And in fact, resiliency has both components. It really means stay on the air. But if something bad happens and you have not been able to identify that and protect from it in advance, get back in as quickly as possible. So get back on the air is what we're all after. Conventional security is an excellent idea and well implemented in the mainframe. It has been for many years. RACF and TSS and ECF2 do a pretty good job of keeping the bad guys out and letting the good guys in to do their work. But as time progresses, the bad guys get a little smart, and they go out and buy credentials on the dark web, or they steal them with a phishing campaign. MFA helps, but it's hard to implement, and it doesn't really help you if people are already inside. If the bad guys are inside the walls, and we're going to talk about how they get there in a second. But you know, one element of that is trusted employees that go rogue. They have addiction problems. They perhaps develop a gambling problem. Then they attack inside. There's also another group that are just trying to do their job. Well-meaning people that make mistakes. All of those should be detected because all of those can take you off the air. But I think in the whole world of cybersecurity these days, those are probably less issues than the elephant in a room. And that is all about the outside attacks. Now, in truth, many people would say, oh man, the mainframe really isn't attacked that often. So what are we worried about mainframe security anyway? Well, everybody knows about the Nordea Bank attack in Sweden, Barclays insider attack in the UK, Standard Bank being attacked again by an insider in South Africa. But what has really changed the playing field is that we're really not thinking about the attack point, because the attack point, as you will see in a minute, is really moved outside the mainframe, however, with access to the entire network. So I'll go on to that in a little bit. But one of the things that I've been able to do in the last while is do a lot of research with my capable research assistant, Chat GPT. I just asked Chat to go and give me a summary of what happened in the Office of US Personnel Management. And this is more typical of what mainframe attacks look like. There was an open systems environment. It was attached to the mainframe. The mainframe, it turns out, contained all of the data for 22 million personnel, high security personnel records. It is rumored that the Chinese were behind this, and they wanted to know who they could coerce, in Brett's words, inside the security structure so that they could have secrets revealed. Well, the mainframe, through data exfiltration, very nicely coughed up 22 million records. And I suppose they have all the data that they need. It's not known if that caused any real problems at this stage, but I suppose in a cyber warfare context, it would be real problems. Probably the biggest one that people have maybe heard about or not is either Anthem or Equifax. In both of those cases, the data that was stolen, in the case of Anthem, it was about 78 million records. In the case of Equifax, 147 million. And both of those cases, the attack came on open systems and because the open systems environment had connectivity to the mainframe and could transition from the mainframe into, from the open systems environment into the mainframe environment, the damage occurred on the mainframe. Now, let me make this perfectly straight. We're looking at a tiny little amount of money here, 16 million, which is the largest HIPAA fine ever handed out to Anthem. But the real cost, according to Al's calculations, my calculations, is more closer to $1 billion or perhaps more. In the case of Anthem, the litigation launched by 43 state attorney generals lasted for 5 years. The settlement was about 129 million. Again, a peanut in the overall cost of this environment. The other things that came up in that environment were, in 5 years, how many security consultants do you think you had to pay? How many lawyers to fight the litigation do you think you had to pay on your side, let alone the costs for all the attorney generals? Try to imagine 5 years of litigation. Every day, your lawyer comes to your operations team and asks the same questions 43 times about how you screwed this up so badly. The consequences of this damage occurred on the mainframe. So if you're thinking mainframes aren't really all that, are pretty secure and we don't really have to worry about them, well, just worry about your job and your company's welfare and how they will be able to run with a mainframe that is for some significant period of time unavailable. In fact, today, you could probably go ask the United Healthcare guys, except for the fact they're really fairly busy after a month and a half, still trying to recover fully from the attack that took place there. The attack that took healthcare payments out of the American system for 5 days consecutively. And although the detailed analysis and all the fines and all the costs won't be known probably fully for another 10 years, they're already, according to their own numbers published within the last couple of days, nearly $1 billion. So I'm going to say on this slide, thank you very much to ChatGPT for looking after these things for me. So I'm going to reiterate one more thing. We're in a brave new world. Remember when mainframes were dead? You know, that was the happy period of about 25 years where we didn't really have to worry about too much, and we didn't have to do too much to mainframes to keep them running. Just keep them up, and nobody's going to pay much attention to them now. But now it's different. Now we're talking about hybrid systems. And that means we're connecting to open systems and they're connecting to the web so that we can get all kinds of wonderful stuff moving back and forth. But it means those open systems can talk to the mainframe. So attacks may be on Windows or Linux, but the big damage is on the mainframe. And the big damage comes from lateral movement. These systems, because they're pushing data here and pulling data there, have access to things. If I break into this open systems environment, I open up the mainframe in a very meaningful way. And the last attack a couple of months ago on ICBC, the industrial and commercial bank in China, paralyzed trading of US Treasuries for several days. And in some cases, some of the participating banks were billions of dollars offside. And that was because of, they didn't even get as far as encrypting things on the mainframe. They just compromised this open systems environment where the trading started. If these hackers had been ever so slightly more clever, they would have done the usual thing and ransomed the mainframe by encrypting something that was valuable on the mainframe or data exfiltration. And now that's not enough either. Now we're actually taking open source, which is the weak link in the open world. And people are saying, let's build applications faster with open source. We can put them on the mainframe, and the mainframe will be much more productive. Well, it will be more productive, but at what cost? Open source is a guideline, a map for attacking a mainframe. What do we do about that? We say file integrity monitoring is absolutely critical. Why is that? Because we can identify malicious system changes, period. So what does file integrity monitoring sound like? It sounds like this. Take a snapshot of your system when it's operating really well, and we're going to call that the trusted environment. It's running great today. I want to make sure that it doesn't get compromised tomorrow. So I captured the trusted state. However, the trusted state continues to move because you got application guys, you got system of ZOS components being changed for perfectly legitimate reasons, and they will go through a standard deployment process. So the software that you get simply has to take that snapshot through some type of auto discovery to begin with, and then learn about the changes as they go through your deployment process. That way, every subsequent scan can produce a new list of what's on your mainframe, and anything that is not on the whitelist or the list that's maintained from auto discovery plus the learning, anything that isn't on that list is a problem. It came in from some unknown or unauthorized source, requires investigation. That means you'll need a forensics browser. You need to be able to investigate the situation. And then we get into, okay, something actually changed. We didn't prevent it with FIM plus or anything else in the environment. So what do we need to do? We need to go get back on the air fast. And that means a surgical restore of the software to its trusted state. You can't do that if you're going to regress everything. You have to selectively pull the components back that were compromised. File integrity monitoring understands what was compromised, therefore knows when and what to recover. So if you automate that process of recovery, you'll get your system back and it won't have malware on it anymore. This is the anti-malware cure. In addition to that, you'll need to get your data back. Everybody understands that part. But immutable backups are not so easy to recover from. They're terrific from a backup standpoint, but not as good on recovery because it requires detailed knowledge and understanding, and sometimes a little bit of hunt and peck in order to find the right one. It's better if you know right off the bat the right one to go to. So, what are the ransomware threats? Typically, attackers put in multiple backdoors. They want to install time bombs. They want to compromise backups. Again, darn good reason to have immutable backups in place. They encrypt the database is very typical in this environment. And then they get the heck out. And they go on to the next customer. So now that attacking is a business, they have software that they've bought on the web or rented on the web or costs shared with the writer of that software on the web. That was the case with Lockbit at ICBC. It is the standard way people attack any environment now, including the mainframe. But there's a new element in here, and that's AI. And AI, it turns out, can write a very nice encryption program for a ZOS platform that will run completely unauthorized. And you can ask dear old ChatGPT to write your program exactly like that, and it will happily do that. So the problem here is that we've been protected to some extent on the mainframe because they weren't connected to anything that anybody would break into. But now they are. And the other small problem is that AI gives them the tools to do some real damage. So in addition to FIM, which will identify malware and allow you to remove it, and it will identify it at an early enough stage that it will prevent the attack. If something slips through, we need to be able to continuously monitor for the kinds of things that are going to be characteristic of that sort of attack. One of the things that hackers love to be able to do is to escalate their own authority and or privilege. In doing that, they can reach into any ZOS address space. They can turn RACF off. They can turn SNF reporting off if they get to an authority level where that's allowed. So what you have to do is continuously monitor for authority changes. What we can do with software these days is compare where the address space started or the task started on the mainframe, compare the authority it had then with the authority it has a second later or 2 seconds later. And if we can identify that, then you could either use countermeasures and say, oh, I'm sorry, you came in problem state. Since you have assumed or escalated your authority to a higher authority level, we're just going to switch it back to where you started at problem state. And then we're going to report that. That's the kind of things that continuous monitoring can do. Again, prevent the problem. After I get a higher level of authority, I can start to cause damage. If I detect the fact that authority has changed in the first second, even the fastest hacker won't actually be able to cause a real problem. That means we can intercept also malicious encryption. It doesn't need authority, but it does use the hardware assist that's available on all ZOS systems these days. We can determine in the first second of operation that an malicious encryption is in process. Then it allows us to suspend that specific task. So with encryption, it can be defensive or offensive. If it's defensive, that's a good thing, and we're protecting the data on the mainframe. Those events and those encryptions are known in advance. So again, we can create a whitelist of all things authorized. So when we see something that's not on the whitelist, since we can detect that encryption in the first second, and if it's not on the whitelist, suspend it. Then we've actually taken two elements out of the time frame here. One is the usual length of time on a mainframe to detect encryption, which is around 30 minutes, and the amount of time it takes a person to react to the fact that an encryption, a rogue encryption, has been taking place for 30 minutes. Now that could be another half an hour, or it could be, a couple of hours, because I don't exactly know what to do. But I'll tell you how this is going to be communicated. Since they encrypted something that's valuable, like a DB2 database or something like that, probably DB2 just fails, and you're left scratching your head as to why that took place until the ransom note comes in. There are many other things that you need to identify, but eliminating this human response time, giving the support team the time to react appropriately, is very important. At absolute best, SMF is minutes or hours too slow in reporting and too slow in alerting. So the time frame of attack. There's a reconnaissance phase. There's a phase where you insert malicious code. There's a phase where you encrypt. Then on the response side, there's a phase when I have to figure out what the heck was going on, situational analysis. Then I have to get my data recovered at the same time, hopefully, that I'm recovering my infrastructure, my trusted system environment. The objective is to get back on the air quickly and have fewer postmortems, corrections, excuses to make, lawsuits, etc. In our environment, we say continuous monitoring plays into this reconnaissance phase, but it also plays in over here when bad things are starting to occur, like an encryption. When the malicious code is inserted, that's typically in the phase before the attack takes place. But then at some point, perhaps there is an attack. Then you need forensics. Then you need that instant information to be available. And furthermore, if you do that well, you can make the entire recovery disappear. But the issue, as always, is you cannot depend on being able to prevent everything. So in the case where something bad actually takes place, we need to do that situational analysis in less time than we've ever done it before. That means a GUI-based forensics environment that knows a lot about what was going on and tells you things that are not commonly available in ZOS. That's how you react quickly. Then you have to get into the data recovery. Well, the data recovery is going to be a heck of a lot easier if you have something like data backups that are immutable and only 15 minutes old. Otherwise, you're going back to backups that are maybe yesterday. Maybe that got compromised, so maybe the day before. This is a big change to the environment. And then you need to get into the recovery phase. Fortunately, recovery has gotten a lot easier. If you know what you need to recover, which comes from all the information available in early warning and detection and forensics, if you know what to recover, you're a long ways ahead. If you can do the recovery at a data set level, your recovery will be much shorter. And that is available through other vendor products like Rocket and data recovery and IZBR and the IBM environment. So given the right environment, given the right software on your system, those processes can be automated in a very large, to a very large extent. However, we strongly believe that we leave human beings in control of recovery. We just give them automated assist to make it much more likely to be correct and much faster. So in the short view of this, we use the insight that's available internally to get the right data back and to get the right programs and parameters and everything that constitutes your system back in a very short period of time. That's how we make some of the guidelines that we have to, and that's how we stop ransomware in its tracks. So with that, I'm going to go back to an even earlier period, and I'm going to make this fairly quick. But that earlier period is all about the supply chain, DevOps. Let's take a look at a supply chain attack. The most famous one was the Sunburst attack on SolarWinds. What did it include? Oh, it included an attack on open systems, the open system build environment in particular. So very determined hackers built into the SolarWinds product build environment, the vendor portion, before it even went to the client. And for months, they were inserting their own malware in the next release of the SolarWinds product. Then eventually that got delivered to thousands of high security environments. And in that environment, they already had the backdoors in, so they knew how to get command and control over those environments. They were inside for months in the victim accounts. And this brought us to the ability to exfiltrate data, intelligence, and if they had wanted to, ransom. But in the case of the SolarWinds attack, the objective was more intelligence and data than it was actually money from a ransom attack. Unfortunately, the mainframe is in the same place, and it has the same build characteristics, not products, but characteristics. So if you think it can happen over here in open systems world, don't look too far past your own mainframe environment. So I don't like to talk about a problem without at least a little bit of solution to be able to counteract that. So in the building environment, we talk about the CI/CD capabilities. How do you build your own applications? How do your vendors build their applications? Well, at some point, in the old days, I built a system and I tested it out in QA, and then I said, oh, it's working really good, and I get approval, and I go through this lovely 10-step procedure to put this into production, and sooner or later I put it on all my LPARs, and there I am. I got a new application and it's all rolled out, and I'm happy. But if you want to secure this, you actually have to know what you're putting in the package is correct. So how do you think you do that? By having the system learn what was in version 1.0 and then comparing it to what was in 1.1 and looking at all the elements that changed. So let's say there's a new application rolling in. Let's say there's 10,000 change components. there is no way that in the peer review meeting, each one of those has gone through. And in truth, probably even after you put better software security, probably 1 in 10,000 or 5 in 10,000 or 10 in 10,000 things that have been compromised don't really stand out, but there is a chance of catching it here for sure. But it gives the peer review committee, the experts that are involved, an opportunity to do change analysis and determine if all the components are correct. Well, they may or may not be able to do that completely, but it is of real benefit that we go through that process. It's more rigorous, much more rigorous than what's currently available. So then we're going to want to go and roll that out. Okay. There's also a period of time in here after it's been updated, before it's been deployed, where changes can be inserted. But we're actually, in this model, we're actually asking management to approve this once we've locked down what's in that software release and what it's capable of. So again, nothing more changes. So you use the same old deployment process. You add one step, and a one step says, by the way, when you go to put this into production, verify that what was on 1.1 over here, which you approved, is still what's on 1.1 over here. That way, when I put it into production, I can run one more test and I can be sure that nothing gets screwed up in the deployment process either. So I know, verified, that what went into production over here was what came directly out of QA over here. So Monday morning, after the application goes live, there won't be a whole bunch of finger pointing about who did this. We'll know that everything got transitioned into the production environment correctly. So the only problem can be in this process here. Additionally, if you decide you have to back out, you can verify that the back out was complete in the same way that you would verify that the roll forward was complete. But if everything goes according to plan, I just simply run my deployments on my other partitions and I'm finished. So lots of things are exactly the same, but lots of things are much better in that environment because I have more control and more knowledge. So I'm going to finish off here by saying a little bit about CyberShield and the NIST framework. The NIST framework is very important, and it's a very good guideline for what has to happen. And we've seen how some of these things fit into the overall cybersecurity framework. And I think Brett did a very good job of showing you how the storage complex knows things that identify issues that will be manifested later in production. So those are very important things to be able to have. But there's more to this solution than what is required. And that more is now there's now some teeth being put into that by DORA and other tools. DORA requires you to prove that your recovery capabilities, your protection capabilities are up to snuff. The requirements are mostly the same as what you see in the NIST cybersecurity framework, which is just out in its new version 2. In that version, it's a very good list of everything that you should be thinking about in terms of the 5 main pillars, which start with identify and go all the way through to recovery. It's a very complete set of requirements, and it's been customized. It's US based, but customized for every country of the world, more or less, and used in most countries of the world. DORA puts some teeth in that. First of all, for financial installations, a 2-hour recovery window. I can imagine that DORA is going to expand beyond Europe, into the UK, into the US, into all Western environments, because it's such a sensible thing to do. If you don't test your recovery capability, if you don't test your protection capability, how will you know it's going to work when you need it? Well, you don't. So it's important that these kinds of requirements are attended to, are put in place, are tested regularly. And that's the rule, that's the role of DORA. Resiliency plans, and that means protection first and recovery second, must be tested regularly, including pen testing. But here's the point. Major fines and criminal charges can result. But this is far smaller. It's still far smaller than the consequences of a breach on the mainframe and the ensuing litigation and the ensuing firings and the ensuing bad reputation for the company and the cost of in the case of Anthem, changing the name of the company and reprinting every single piece of collateral that they have and writing new contracts with 78 million customers. This is not peanuts. The consequences are far worse than the fines would ever be, but the possible criminal charges, if you don't do what's the right thing, the possible criminal charges, how would you like to spend your retirement in prison? Maybe not. So what does it look like? Okay, this is just a different way of looking at the same thing. Identify, protect, detect, respond, recover. Here's what we think the answer is technologically. A multi-vendor approach that brings in software and hardware working together so that you know what was affected if there's a problem. You know when it was affected. You can take the right steps quickly. You can be, people of lesser skill can be guided through the process. But we start at the very beginning with knowing what to trust, with backup verification, with learning software. That's what's required on the technological level. These fill the gaps that have existed in z/OS forever. But more importantly, I think, is it needs an end-to-end multi-vendor solution. And that has to be available for people that don't have 40 years of experience on z/OS, because that's a vanishing species. Younger folks just aren't going to react with z/OS in the same way that we did in the youth of the operating system. But it has to start with identify, and it has to bring the newer people with a lower skill level all the way through to being able to do the recovery more quickly than you would ever do, even with experienced people and manual processes. It has to guide them through the right steps so that it's done with more precision. And that, I say to you, is how we fix the gap in the human element of an attack. So that's pretty much a wrap for me. I really want to focus on DORA, on NIST as good guides for how we can go through and how we can make the mainframe the bastion, the most trusted, the most secure environment that there is. Many of the functions that we've talked about have only recently become available for z/OS. They are not available on most other platforms. We can make z/OS the most secure platform that exists. And that's what we should do. So as customers, I would ask you to demand that your vendors work together in a process that begins with identifying and preventing problems and ends up with a highly disciplined recovery process that includes both getting the system components back in an anti-malware state and getting the data back and the forward recovery that's necessary to bring it right up to the minute. But just try to imagine this. The difference between being able to identify a problem occurring in a few seconds and the recovery required and associated with that, or a few hours, or a few days, or in all too many cases, a few weeks. That's what ends up in court. That's what ends up with punitive reputational damage, not only for companies, for the individuals that did not take action. So I would ask you, do you not think that you should take action now and prevent a problem before it occurs, rather than waiting for you to become the victim and your company to become the victim? And on that cheery note, I'll open things up to questions or terminate the session. Brett, any parting comments from you?
No, I really enjoyed that presentation. Thank you, Al. There are no questions that I can see. Nope. So thank you very much indeed. I'll stop the recording and see all you folks tomorrow.
Perfect. Thanks very much for your time, folks.